Finishing up 2.1 Internal Structure of Earth. So how do we know about the internal structure of the Earth anyway? We did not journey or drill to the center of the Earth. Most of our understanding comes from seismology, the study of earthquakes, and in particular seismic waves. As seen in this picture, earthquakes cause seismic energy to move through the Earth. Some waves, P waves, move through solids and liquids. Some waves, secondary S waves, move through solids but not liquids. So you can see how we can differentiate between solid and liquid layers of the Earth. Also, the speed of the waves vary, which gives us information of the densities and compositions of the different layers. At layer boundaries, some waves are reflected and refracted, identifying boundaries even more clearly. In the mantle, travel times for some seismic wave pathways indicate that the waves travel faster the deeper they go, indicating a change in composition and/or density. In the core, P waves travel considerably more slowly as compared to the mantle, and there are no S waves, which indicates that at least the outer core is liquid. Information on wave movement gives us a picture of the inside of the Earth. In addition, seismic waves have shown us where magma is generated in the asthenosphere, the existence of slabs of lithosphere that have apparently sunk deep into the mantle, and the extreme variability of lithospheric thickness, reflecting its age and history. Consider this. How can seismic waves show us the location of liquid magma? Consider this. How can seismic waves show us the location of cool, rigid, lithospheric plates in a putty-like mantle? Plate tectonics. Plate tectonics is a unifying theory that explains many geologic phenomena. It explains large-scale geologic processes that deform Earth's lithosphere, making ridges, trenches, mountains, basins, oceans, and continents, etc. These processes are driven by forces within the Earth. A pre-plate tectonic theory was proposed by Alfred Wegener in 1915, called continental drift, but it wasn't until seafloor spreading was discovered in the late 1960s that the theory of plate tectonics was formed. What is plate tectonics? It explains that the lithosphere is broken into pieces called lithospheric plates. These plates move relative to one another and are created and destroyed. In this picture, we can see several lithospheric plates and how they move relative to each other. There are also the three types of plate boundaries: convergent, with the red teeth, where one plate is subducted and destroyed, i.e. melted, beneath another plate; divergent, with the red arrows pointing away from the blue line, indicating the plates are moving away from each other, and new lithospheric plate is being created at the boundary. Transform, with the red arrows pointing past each other, where the plates are moving past each other. The numbers indicate the relative movement of the plates in millimeters per year. Take a minute to look at the map. Where are plates being created? Where are plates being destroyed? Where are plates moving the fastest? Boundaries between lithospheric plates are geologically active areas. Plate boundaries are defined by areas of seismic activity, earthquakes, and volcanoes. This picture shows many earthquake and volcano locations. Notice that the plate boundaries are delineated by the earthquake and volcano locations. Tectonic boundaries are also delineated by physical features. This picture is of our Earth and is color-coded for elevation. Black is the lowest elevation, through blues, teals, greens, yellow, browns, and gray-white as the highest. We can see the teal-colored Mid-Atlantic Ridge, which is a divergent plate boundary, rising high above the ocean floor. We can see the high Himalayan mountains in a convergent plate boundary. We can see the deep Marianas Trench and other trenches at convergent plate boundaries in the western Pacific Ocean. We can see the transform plate boundary on the coast of California. At the mid-ocean ridges, new crust is added to the edges of lithospheric plates at divergent plate boundaries. Crust is destroyed along other plate edges at subduction zones at convergent plate boundaries. The Earth's size remains constant, never growing or shrinking. Sinking ocean plates are wet and cold. These cold plates come in contact with hot asthenosphere, as seen in this picture, where they begin to melt and generate magma. The magma rises to produce volcanoes. Earthquakes occur along the path of the descending plate. This plane of earthquakes dipping into the earth is called the Wadati-Benioff zone. So for review, what are some types of movement along tectonic plate boundaries? Think about it. Did you get it right? Convergent, divergent, and transform plate boundaries. Now consider what type of plate combination might be involved. We'll discuss this next. Here is a table of different types of plate boundaries and the different types of plates involved. You can pause and review the table now or find this table in your book. We are going to briefly look at each combination. First, divergent plate boundary, Mid-Atlantic Ridge. These pictures are on Iceland, which is an island on the Mid-Atlantic Ridge. These next pictures are a divergent plate boundary, the Great Rift Valley. Where the plates separate, it is usually a low-lying area, so often water collects right where the plates are separating. Next is convergent plate boundary, continent ocean. The Andes Mountains. The trench is just off the coast of Chile, where the oceanic plate subducts under the continental plate. The continental plate is affected and crumples up to make some beautiful mountains. Next is convergent plate boundary, ocean-ocean. Solomon and Vanuatu Islands. The older, colder oceanic crust to the west is subducting under the younger, warmer oceanic crust to the east. As the old, cold oceanic crust melts, the magma rises and produces volcanoes to the east of the trench, which supports a nation. Next is convergent plate boundary, continent-continent. Himalaya Mountains. Neither plate wants to subduct, producing our highest mountain range. Can you see the folding and crinkling of the mountain range as Indian continental plate is reluctantly drug under the Asian plate? Next is transform plate boundary, San Andreas Fault. The coastal part of California is being sheared off and taken north as the rest of California moves relatively south. See the faults in the pictures? Plate motion is geologically fast. Plates move on the order of a few centimeters per year, and that movement may not be smooth or steady, resulting in earthquake felt by many. Plates can displace by several meters during a great earthquake.